All right, so this is Heather. Heather is kind of like our chief content person. She wrote lots of the content that's included with Virtual Labs. And so she has taught in the past physics. She was a chemistry and physics student at Brigham Young University. She helped me develop the physics lab years ago. She did most of the algorithms and databases that we needed um, for for the physics labs. Chemistry was developed before her time, and so anyway, we're welcome. So I think what way we'll run this is. So I'm Brian. I'm Brian Whitfield. I'm a professor of chemistry at BYU. I've been there for 22 years. Like you know, I went to graduate school at Berkeley, did my undergrad at BYU, and then I've been back at BYU here. And so I developed the labs. I had the idea as a graduate student at Berkeley when I saw students going through the labs there for Chem 1A and cookbooking their way through and absolutely learning nothing. And maybe the professor who was teaching it wasn't so great either, but his name was Professor Jolly, and I like to say he was anything but jolly. And he, you know, I just saw students who were just doing the experiments and not really learning anything behind it. And so that's when I had the idea that, you know, you still need a real lab to teach technique, but my idea is that we could create these virtual environments that were open-ended enough to allow students to make mistakes and not have to give students as many instructions and procedures and let them kind of figure it out more. And so I'm all about students figuring it out on their own and trying to learn with enough structure and guidance that they don't get discouraged and lost. And so that's that balance of unstructured discovery, but with enough structure, depending on the level you're teaching, that students don't get feel like it's hopeless, so that it's actually fun. So that's kind of how it started way back in the early 90s. And so we developed all these labs at BYU. They used to be sold by Pearson for many years, for about 15 years. And now we've taken all of those licenses back, and we've been updating and improving the labs. And we're in the middle of a HTML5 development. We're going to start releasing some labs here in a few months, but that doesn't help us in our current predicament. So we'll make do with what we have. All right, so we're going to run it. Heather's going to monitor questions, and probably easier to kind of type them up, but you're also free to go in and just ask a question, and we'll try to do our best to answer them. I'm going to kind of go through and explain how the client works and the philosophy behind what we do, and then go in and do some demonstrations. So I see that we have chemistry, organic chemistry, and physics. So in the hour, that means I'll probably have to do, you know, not so detailed of a level and everything, but that's okay. All of the labs kind of work the same way. They just have their own focus. So,
and you can always watch the old webinars and the old videos online to catch anything that you still have questions on.
all right. So I'm going to start sharing my screen here. And launch the client here that we have. All right. So our labs are pretty, what I would call, they're highly realistic, open-ended labs. And you know, they've been through about 4 different iterations over the last 20 years, and different graphics and different platforms. They currently run on 64-bit Mac and Windows 10. We also have an Android version of general chemistry and a beta version in Android for physics. There's a few graphics glitches in physics, but it works. It's just a few graphics issues that we don't understand yet. So we have these Android versions that are meant to be downloaded and installed on Chromebooks. However, you can't just access them Google Store has a lot of restrictions, so we really can't make them available that way. So the way that the Chromebook version is available is usually through a managed Chromebook system, like at a school district, where we provide the Android builds, the Android apps, and then the manager administrator will then make a private download for the students, and they download them and use them on Chromebook. So we're working through trying to find a solution for the open-ended Chromebook user that isn't attached to anybody. We're working on that. That's one of our goals this week, but we're also being hit by huge number of users on our server, so we got to solve that problem as well. So just to let you know, Mac, Windows, Chromebook. Chromebook does not have this client that you're seeing on the screen here. It just kind of is a standalone app for general chemistry and physics that just launches by itself, and it has a kill switch in it that's going to shut off like next July 2021 or something like that. So it's just a way. It's just a way of managing our apps. So the way that client works is it downloads, you install it. Once it installs, most of you have probably tried it out. It installs, and then it updates itself and installs its worksheets. And it's divided into these 4 different tabs of labs, worksheets, license, and settings. So the labs is where you access the different virtual labs and lab products for chemistry, organic, biology, physics, and physical science. And worksheets are where we have a set of lab activities that are geared to different levels for high school, higher ed, mostly some middle school as well for physical science. And these lab activities are in the form of PDF files. So if I were to go to general chemistry, go to higher ed, they're organized by these different topics here. And so if we were to go into acid-base chemistry, you would see concepts and acid-base titrations, ranking salt solutions by pH, and a whole series of different types of lab activities that might be interesting to you. And so so these are all structured to be at different levels, like introductory levels to more advanced levels of activities. And so you click on here, brings up a worksheet here that shows background, and then it gives you the procedure. So these worksheets are a great way to learn how to use the software, because they give you step-by-step instructions, and then they give you assessments. And like this one is really short, really easy. It just says, here's a titration. It's all set up. All you have to do is run it and have them go through a calculation, and then they're done. So, and then we have much more advanced, like here's an unknown, and where we might give them fewer instructions. And so these lab activities, we have about 80 of them for general chemistry, and for organic chemistry, like 120 or so. And so this is kind of where the hub is. These are the lab activities, but our metaphor is imagine you had a real lab with a door. You go in and there's a bench, stock room, equipment. You would need to develop procedures and assessments for the students so they could take advantage of the equipment in that room to do the learning objectives. And so that's what we have here, that these are this is the pedagogy, the way for students to go do it and learn, but you're not restricted to these. All right. So you can write your own, modify these, doesn't really matter to us. This is just a drop-in solution that make your life easier, and just hand it off to the students. Here's the license tab. So when we give you a code, this is where you put the code here and you submitted it, activates it for some length of time. So my code's going to expire in April. Since all of you are higher ed, this is where we change the settings, but it doesn't really change the lab. It just changes the settings for the worksheets, and I'll show you how that works in a minute. So this is just the client. It's kind of the central place. It manages the licenses and gives you access. So, so what a student would do, or what you would do, is you'd click on general chemistry. Notice I've already got it set to higher ed. And so it launches the lab, and this is our landing page. So each one of these icons here represents a lab bench. So imagine a lab bench in a lab, and that lab bench has a self-contained, independent simulation of everything that you could do in that lab. So if I click on titrations, for example, um, it brings me to this lab bench, and notice there's no avatars, no bubbles. It's like a real lab that we have to provide the structure and instructions to students to know what to do. And so we have drawers full of beakers, different pipettes. We have a conductivity meter, a pH meter, pH probes, standard buffer solutions, water, analytical balances. And then we click on the stock room, and then we have shelves full of acids and bases and reductants and oxidants to do different types of experiments. We even have an inert salts to see how inert salts could, say, modify the equivalence point of a titration, for example. And so we also have clipboards. So all the labs kind of work this way. Clipboards have presets. So we have a way of presetting the lab. So for example, if I did a weak acid, strong base, I've preset the lab so it's all ready to go. So here the student can focus on what a titration is and not how to set up a titration. So here's a pH meters in, the conductivity meters in, here's their meters, there's their values, there's the meniscus. I've got sodium hydroxide that's in the burette, and I've already pipetted 25 milliliters of acetic acid. They have a known concentration and a graph here, and I can just go ahead and start titrating and control the rate of what's going in. I can click save, start saving data to a lab book that's over here. And so here's the conductivity, here's the pH, and now we can just, before we even dive into doing a titration, we can have a student do a overview of what it looks like and what the pH curve is looking like, and lots of different types of things. So it's not just here, do a titration, it's all the aspects associated with a titration. So we have different indicators, indicator chart, so they can choose which indicator. And so I could click here on stop my recording, open my lab book, and then here is all of the data that they collected. Here are some instructions that came with that preset that appear here in their titration. Appear in their lab book. So this is what you do. So you can have this preset, but you can also, all of the labs work this way, is you have presets to kind of focus on certain experiments, but they're also completely open-ended. So I could pull out my beaker here. I could pull out a 25 mil pipette and just start doing the whole process. So what if I wanted to do, hydrocyanic acid titration? Take that, pull it over here, pour some into my beaker, and suck it up into my pipette. Now I have 25 mils, so I can dispose of this over here, bring in another beaker, pipette it. Now I have 25 mils. Or add some water to it, put it on the stir plate, turn on the stirring. Then I need to choose, my thymal blue maybe we'll add. So we'll add that. And so there's the right indicator. I could turn on the pH meter, conductivity meter, add this. This has already been calibrated because the previous experiment did that. And take in my conductivity. So you can kind of see how it all works. So I have sodium hydroxide. So what if I wanted to titrate with ammonia? It's probably not a good choice because it's such a weak acid, a weak base, but I could do it. So I come over here and fill that up, click on it to open. I can click on my graph, and now I can go do it. I can go do this titration and decide how it goes. So, and then they can learn. So we allow all the different permutations, and then they get to experience the consequences. We can also, of course, weigh the solids. So I just showed you how one bench worked. All right. They all work that way. So going back to those worksheets that we had, corresponding to each of those worksheets is this same list of the worksheets over here. So what if you assigned Rutherford's backscattering experiment worksheet? Okay, what a student would do is they would come in here, find that same worksheet in this list, and click on this and open it. That's why we have high school and higher ed, different levels, because it changes what this preset or this table of contents for these worksheets are. And so for high school, we have a different set of worksheets than we do for higher ed. And so, or for AP. And so you can just change the level by clicking in the settings, and that gets us here. So let's say that we assigned Rutherford. Maybe we're teaching atomic theory, and so we want to do the Rutherford experiment. So this is an example. So titrations is an example of, highly likely an experiment that you would do in the real lab, okay, in some form. And but atomic theory here is something that you're not likely to have been doing in your real lab, but it's something that you can now do as part of your lecture or part of a lab experience, is to have them really explore atomic theory. So here is the Rutherford experiment. We have alpha particle source, we have a metal foil, and we have a detector here, which I turned on, which is the phosphor screen right here. And so I'm doing Rutherford's experiment. I'm putting alpha particles through a metal foil here, and then I'm detecting that with my phosphor screen. But I can do anything I want. So what happens if I decide to move my alpha particles over here? Well, look at this. I'm still shining them into the gold, and they're deflecting off in some amount, but a totally different type of result than if I'm in the front, right? I can move my detector screen anywhere I want to, like over here, or I can move it here to the side and say, hey, maybe there I get one. Now I got another one. I can go into persist mode and save where they hit and start doing some statistics. You can actually, if you wanted to, our worksheets don't do it, calculate the cross-sectional area, the scattering cross-section for gold, for example. So I can move it back. So this, we have a worksheet that steps them through this experiment and steps them through the deductions that says the atom is mostly empty space. So it's not just doing it. We have the assessments that guide the student into an understanding of what this is. Now, they could also, for example, say, hey, what happens if I don't want to use gold? I can return it to my stock room, double click. I can open up my box of metal foils and pick another one. So what happens if I pick, I don't know, let's just take copper, for example. So now we have a copper metal foil, and I put it in front. So you notice here, the spot's a lot different than gold. I still get scattering, but it's not nearly as much. And so this is just an example of the open-endedness of an experiment in atomic theory. This data that you're seeing here is real data that we collected off a real backscattering experiment. So this isn't predicted. This is everything we have is real data, or the best models that we have. So you click on that, reset the lab, and then here's your stock room for the for your quantum lab for atomic theory. Is we have lasers and electron guns and super light bulbs and different detectors like spectrometers and video cameras, two-slit devices, liquids and gases, and then you can have magnetic fields, electric fields, and heat things up, oil mist. And again, we have these presets. So here's Millikan oil drop for experiment. Adjust the electric field and move your drops around And then from that, you can calculate the charge on the electron. Or we can go do two-slit diffraction, change the wavelength of your laser, or change the slit spacing of your two-slit device, or change the power of your laser, and see how it affects your diffraction pattern. And so we have photo emission for hydrogen, photo emission for all these different gases, HCl, Raman scattering even. Obviously, that's not something we do in general chemistry. It's something that we could do in PChem. And so photoelectric effect. All right. And so just shows you an example of all of these different kinds of things. So let
Could you
me,
jump to OChem?
what?
Can you jump to OChem? There are a couple of requests for that. And then we can come back to general chem if people have questions, but could you show how OChem
Sure.
works?
All right. Same idea in organic chemistry. We have lab benches, and organic chemistry, we have worksheets, the same thing, but we have the lab benches are divided into synthesis and qualitative analysis. All right. So, and so in the synthesis lab, what we do is we have this lab bench, and we have these different named reactions. All right. So a named reaction defines a set of starting materials. So it doesn't say force you into that reaction. It just defines starting materials that you would need for such a reaction. So if I wanted to do a sterification, I can click on that, and then that defines here these liquids and a solid, different starting materials that I can choose. So what we do is we allow you to choose any of these starting materials, none of them one or two, any combination, any order. We let you choose a solvent or no solvent, and we add it to our round bottom flask here to so you can set up your synthetic reaction. So you should have in mind, the student should have in mind a target. That's what the worksheets do. The worksheets say, here's a target, and what do you need to do to make it? So they have to choose the right starting materials. They have to then choose the right solvents, and then build the right setup out here. So if I were to try to make something, I would choose this acid, and then I would choose maybe this alcohol, and I can have a solvent. I'm not going to choose the solvent. I take my round bottom out here. Notice that my stock room shuts down, so you can't select anything now. And now you have these 14 different reagents that you can choose from, and they can choose any of them. And we're going to have an outcome for what the reaction does. So for any starting material combination, for any solvent, for any of these reagents and any of these reaction conditions, we will have what the product is going to be with the right kinetics, with the right rate constants to show you the time. So I could here, for example, to do a sterification, I would add my sulfuric acid. Now I could run this reaction as is, or I can add a condenser, and I could add my heat. And for this case, I'm going to add nitrogen as well, because I have to vent my system. And if they didn't vent the system, it would blow up. So we have outcomes for that. And so, for example, if you ran this for like 24 hours, it might start converting into tar because of the acid in there. And so now we're ready. So I've added my acid, I have my right setup. Then what I do here is I start my reaction by clicking on my stir button, and reaction's going. So how do I know what's happening? Well, I have my chalkboard, which they don't normally have, but the idea here is to guide them into how would you know. So I would, for example, grab my TLC, and then that would give me my TLC here, and my starting materials in the TLC of the product mixture, right? So I could save that to my lab book, press OK, and say, hey, I need to go advance 20 minutes and let's go see how far my reaction's gone. So, hey, I'm almost done. So I'm going to save that. You know, I could go to my lab book and say, you know, type in here and say 5 minutes, and then come down here and say that was 20 minutes or 25 minutes, I think it was. And then go advance in another 10 minutes and say, wow, it slows down as I get close. So I'm there. By doing the TLC, I can save that and say, you know, come to my lab book, for example, and say, you know, 1:12 p.m. is when the reaction finished. And then I'm done. So now I have to work it up. So I take my sub funnel, drag it in on top. Now I have my product mixture. Now I can choose my correct aqueous reagent. In this case, it really doesn't matter, but in some reactions it does. And you can do counter-current extraction. So you could say add a base, drop an acid into the aqueous layer, extract out the organic layer if you wanted. So I'm going to go add water, and that gives me my organic layer and my aqueous layer. And I'm going to take my organic layer, I could put it here, or I could put it back on the stir. And so let's say that if it was a mixture, I could put it back on the stir here and add my distillation apparatus to purify it. So let's get rid of my sub funnel. So I got rid of that part. I didn't have to. Now, how do I prove? So the chalkboard says I made it, but how would I verify that? So we would have, so we just take the NMR. So I took the NMR tube here, dragged it over. And so I now show the NMR of this. So I could zoom in, I can count the peaks. These numbers represent peak numbers down here. So these are the integrations. So 1 and 2 and 3 here. So you have these different peak integrations. I can save that to my lab book. I can go to, depends how advanced you are, I can go to carbon 13, drag my carbon 13 there, and save that. You can do mass spec, drag that, see a mass spec, save that to your lab book. Say, okay, do FTIR. So these NMR and the FTIR data are real data. We acquired them from Sigma. And so they can use this for practicing how to interpret their thing. So it's not just, here, prove it. They have to identify the peaks and know what the peaks get assigned to and things like that. So that's how a synthesis would work. There's like 5 million different outcomes. Most of those are no reaction, obviously, but we allow for all of those. So we have ice, and we can ice reactions down, all these different reagents. And
excuse me, when they're saving the data, where is that going, and how would the teacher see that?
On the lab book?
Yeah, so where is that now?
Excellent question. So
yeah.
it's
Questions
right
on
here.
that. So go into good detail on that, Brian.
So this is all that data that I've saved, okay? It's all here in the lab book. And then what the student would do is they could, if you wanted to see it or they wanted to come back to it, they could come over here to File and save it under some name. So I'm going to save it to my desktop. And then let's say that I were to exit the lab. There's that lab book. Now, they can't open it. There's no other programs out there because it's our proprietary format for all of this data that we have to protect because of copyright issues with the spectra. But what they could do is come back to organic chemistry, open it back up, and they could click over here or go into the lab or click on their lab book, and you notice that it starts clean, but they could come over here to open and open that back up, and then they
Which
have
is also what the instructors can do, right? So students
Right.
can then submit those files to you as instructors through your LMS or through email, and then you can see all of their notes.
So, for example, if you wanted the lab report in PDF format, how would can they translate that to a PDF file and upload it to, or would you, how would that work? In other words, like how
So-
would they submit the report?
So there's two routes for submitting. So there's kind of three different routes that people use. You
Oh,
could keep everything here inside the lab book and say, this is the report, and upload this file to your LMS if you're kind of on a, or email it to you. And then you or the TAs would open these and grade them and give them a grade based on what's in this. That's option one.
okay.
Option two is we have worksheets. So we have these worksheets. So like here in, go to organic chemistry, and we have these 120 some odd worksheets. So this is the one I always recommend first, using thin layer chromatography. This is always the first one that we have them do, is it does step-by-step on doing reactions and characterizing and using that. So this is one of them. So these are lab reports that they could do.
Oh, okay.
So here is like, list your starting material, solvent, reagent, products formed, how long did it take, what's your TLC values, write your mechanism. Here's your, identify your peaks in your FTIR and your peaks in your NMR and stuff like that. So this is a lab report. So that's like option two.
Oh, okay.
Option three, what some professors do is they have the students actually kind of create their own report in Word. And then what I would suggest they do then is, we don't have because of in the agreement to get, 800 spectra from Sigma without having to pay for it,
Huh.
we couldn't let them kind of export it, in some easy way. But what they did allow us to do is let's say that we have this button here to show a spectral library. So let's say that they got this, then what I would do is just take a screen capture of that. And
Okay.
I would take that screen capture and include that in a separate lab report and say, here's my spectra. Here's where I identify.
Okay. Okay, I see. Okay.
Option three.
Oh, okay.
Okay, can you guys hear me?
Yeah.
This is Alex. Maybe I don't have the video.
Well, I can't see because I got my screen covering up my my
Okay.
program. So what's your
Well,
question?
somehow I have my camera on the other side, which I was doing something yesterday. Let me get my camera to the front. Sorry, here it is. Hi, guys. Sorry, I just joined you when you were mixing the sulfuric acid.
Ah.
So maybe my question is redundant. What about the amounts? You mentioned that. I mean, if you did, it's okay. I will find out on my own. If you didn't, if you can please explain that.
So so when we were putting this together, we couldn't deal with the quantitative side of it. I mean, I'm not by the way, I'm not an organic chemist. I only know esterification, okay?
Okay.
I'm a materials and physical chemist, okay? But my colleague, Merritt Andrus, who is an organic chemist, we put this together years ago. And we just found out that we couldn't do the quantitative side of this. So it's really what starting materials do you need? What reagent do you need? And so we haven't put that in yet. We just haven't done it yet.
But the general chem area is very quantitative. This
Yeah.
chem area is not as much, but the general chem lab and the physics and the bio, they're a lot more quantitative activities.
So basically it's very qualitative, right? You take the alcohol and the acid and you put the catalyst, and you got the product and you do the IR and so forth.
Yeah.
Okay. I guess we can possibly give them some, and you do have pre-made labs for, like, let's say.
Yeah, we have those worksheets that you could use as a drop in and say, hey, do this worksheet.
Mm-hmm. So I could see this theoretically being, pursued as follows. Like everybody does this, and they give to each student different scenarios. Like you used, 3 grams of isopetal alcohol, and you use this much, and there's somebody else used 2.5. So everybody kind of has its own report.
Well, you can't change how much you add, but you can say, you can break them up into groups, or you can break them up into, and depending on how big your labs, I mean, our lab sections are 36 students, and you break them up and you just say, here's your target. How would you make it? I think, it depends in what scenario we're in. If we're back in the normal world where we have a real lab, this organic lab gets used as a companion to a real lab. So they do some reaction in the lab, and then you test them on it by saying, all right, you did this lab. Now let's just see you make this product that's a little different. Did you understand the differences? Did you do it right? Or you extend it. But in the current situation where we can't do the real labs, then this becomes a pure lab replacement.
I understand that this is a very powerful tool for what you just said, right? To supplement our regular teaching. And actually, I heard that some of us can go actually do some live experiments and then combine that video with what you have with this program. Let me ask you, can we custom? I mean, so let's say I run the virtual experiment you just described, and I can run it, let's say, 10 times. And, can I record this? I guess I can with my screen.
Mm-hmm.
And then create questions. What did I do wrong in case 1? What did I do wrong in case 3? Like why this exploded and so forth.
Oh, excellent.
The
That'd be
potential
great.
scenario.
Uh-huh. I mean, we can't record it, but you could certainly do a screen recording.
Just a screen recorder, right? So I can
Sure.
see, I'm thinking aloud here, but is that a possibility? I mean, that's something to create lab questions like this or lab quizzes.
Yeah. Or why did this make tar? Or why didn't watch this video. Why didn't I get a product? Or why did I get a mixture? Or why did I get three products here and stuff like that? So that's an excellent way of doing it. And actually, we have a couple of old papers we published in 2005 and 2006. One of them was on this organic lab, and we have some really cool data that shows if the students do this lab before they go do the real lab, they do it in like half the time. And then there was like a 30% increase in performance on the lab exams, just because they understood why better.
Yeah, I can see it working. And also coming to the labs, I mean, your lab notebook, it seems to be optional, right? If we want, we can have the students have a Word document open on the side of their computer and type in their own Word document, screenshot the IRs and the NMRs, insert them like JPEGs, and then transform it convert it to a PDF, and then submit this as a PDF to us.
Absolutely.
Yeah. Okay.
All right. Let me.
One more quick question, then we need to switch to physics.
Well, I got to show them qual a little bit, then I'll go to physics.
Okay, so hold on. There was a
Physics.
question of, is there a way to determine yield other than masses, GC, NMR ratios, et cetera?
No, but we do. So if they stop prematurely, then so we assume, we can't do any of what the theoretical yields are, but if they stop prematurely and they have like they didn't complete their reaction, then the NMRs and the FTIRs and the mass specs are weighted by how much is in there by molar ratios, and so they will get spectra that are mixtures of everything.
Nice.
Okay. All right. Let me show you this side of it really quickly, which is pretty powerful on its own way, is this qual side, where we have these different functional groups and a general unknown. And so, for example, if I click an aldehyde, that shows the structures of 3 knowns, so they know what it is, so they can practice. So if I click on the aldehyde, it shows these 3 knowns, and they can select these, add it to this round bottom, or they can get a numbered unknown. Okay, and we can give you the instructions, the instructor manual that gives you the table of what these unknowns are. So we can add that, and then I bring this out to the cork ring here, and it shows you the boiling point, percent carbon, percent hydrogen, and the unknown number. And now they can do wet chemical tests. So I can take this up here and do it, for example, a Jones oxidation, and we're going to show them a video of what this result is. So we show a real picture or a video. If the timing is important. And so we can do that, and then I can get rid of that, and then we can of course do the we can do these NMRs and the spectra. So their idea is, what do I have? And so we have in those worksheets again sets of these unknowns that they can just report what they are and do a numbered unknown this way. Okay, so that's one way, these numbered unknowns, and we have worksheets that step them through it. We also have the clipboard here where they can go get unknowns this way, where it just defines an unknown and now it's not numbered, so they don't know what it is. This happens to be an aldehyde, so they know it at least has an aldehyde in it. And then they go through the test, and then what they would do is go to the lab book, and then they could go to the report, and they could put in their name of compound, and then click submit, and then it reveals the name. They save this lab book and submit it to you as another way of reporting what their unknowns are. So just two different ways of doing it. I wanted to just show you that quickly. So, so let me show you physics.
Roughly, do you know roughly how many unknowns you have in your data bank there?
More than about 300, I think.
Yeah.
I mean, you know, I guess several aldehydes, ketones, esters, and so forth, right? Yeah.
And we have a general unknown too, where it could be multiple functional groups and pretty nasty stuff as well. So yeah.
As an instructor, do I see a list of the unknowns somewhere here on
Yeah.
the menu?
Oh no, no. That's so we would send you the instructor manual that has the list of unknowns there.
Oh, okay, one who purchased the thing. Okay.
Yeah, just send us an email and Heather
We
will
just
send it
don't
out
want
to
to
you.
release it to the students, so.
Yeah, of course, yes. But I thought there is an instructor version that we see in this student version. Okay.
All right, this is physics. So physics, what we did is we took lab benches. We created 4 lab benches for mechanics, density, optics, and circuits. It doesn't cover pulleys. It doesn't cover springs. We didn't have time for that. But we also include 3 workbenches from chemistry that are physics oriented, that are also part of algebra-based and calculus-based curriculum. So not just necessarily the first semester, but you know, modern physics and things like that. We have a set of worksheets as well for these, but again, this is probably a smaller set than our chemistry, so there's a lot of things that aren't included that you can do. So let me briefly show you mechanics. This is probably the one that would take. All right, thank you. So in physics, this is the one that you'd use a lot. And so I actually taught a physics class once, way back before I taught at BYU, and because my PhD is actually in physics, actually. And so, you know, I just found it really difficult to teach mechanics and motion because I always had frictions. And so I invented this to try to allow students to do experiments in a virtual world where they can control all of their variables pretty easily. So in this stock room, you have objects like a ball, buckets of balls, a sled, a rod. You have forces that you can apply like a rocket, a plunger. You have different gravities, frictions. You have a ramp, and you have a solar system. So the way it works is a student could take out an object, apply a gravity, and they could say apply a friction, for example, and then pick a force. And then they could click here, and then you have a 2D surface here where you can drag out your ball and it gives its position. You can change its units. You can change your coordinate system, change your acceleration, so how fast or slow things are moving. So you can have them control variables like what happens, click start, nothing happens because there's no forces, nothing's acting on the body. So you reset, and now you say, okay, well, what happens if I add gravity? and I click start, and then it falls, but there's no friction, so your acceleration's constant, and here's what your velocity is. So what happens if you add friction like air, and then you can click start and then let it drop and see how the acceleration changes, and you can click reset, and then you can control variables by clicking on parameters and saying, all right, here's my ball, this is what it's made of. So you have different materials. Diameter, you can change the diameter, the mass, how the mass is distributed, initial velocities and angles. You can change your gravity. So I'm on Earth's gravity, you can change it to different planets or type in what you want. You could come here to your frictions and change your elevation, for example. And then what I could do is say, okay, now what happens if I add two-dimensional motion and add a plunger, and then I can click force and launch my force, and then I can track all that. All of this data you could record right here and reset it back. And then I can return all my items and do another experiment. So we have ramp motion. So, and we also have presets here. So here's billiards, for example, with friction, and the elasticity is 0.95. And so I can click force and track what happens here. You can range these balls, you know, up to 16, I think it is. And you can change the size and the mass of the balls or keep them all the same. So that's one. And you could do inclined plane here, rolling ball with friction, and then let it start rolling down the ramp, and then change its angle, change its frictions, change where the mass is, and measure all of that. So trying to find one that's radial gravity sync. So you can put a radial gravity here, put on your rocket, control how long the rocket fires, and have them set up circular orbits or elliptical orbits, you know, or put in friction here. So what happens if I reset, zoom out, and grab my air friction, for example, come back in. Now I can say, hey, what happens if I add in my friction and do that? Well, then I'm going to spiral in and implode in the middle of my radial sink. We also have solar system. So I'll just pick all of the planets, zoom in here, and so what you can do is drag out your planets. So I'm just doing the inner planets. You probably can't see these very well. So I can increase their size so that you can see them better. You can see the shadows. And then what you can do is click start, and I'm doing 1 day every 10 seconds or 10 days every 10 seconds. And then I can change my view onto the plane. I can turn on tracking so I can track where they've been. And zoom back out to the top view. I can, go ahead.
Brian, can you show up optics? Often spring semester is E&M.
Sure. Here's optics.
Or circuits, right? So just showing a variety of them.
So here's optics. What you can do is we have different objects, candles, beach ball, garden gnome. I can take that out. And then I can take out my virtual eye here. And so I can see here. So I have autofocus on, and I can turn off certain colors. I can turn on color blindness so they see what it looks like. And so I can move my eye in different positions to see it, and rotate my eye. And like if I come over here, then I miss it. So I would need to turn this in, and then I can see it from the different perspectives. And so I can look at objects. Now I need to turn my eye back here, and there it is. And then I can put in lenses, and I can put in different mirrors. So for example, I can put a mirror right here, and I can click and drag it. So I have these sight lines, so it helps me kind of line things up. So now I can see both images. And then I can come over here and click on the gear and change, is it a flat mirror? Is it a, you know, does it, what's its curvature? And then we see all these different images on here. And of course you can save this to your lab book and save these images. So you can do prisms, you know, put in filters, have these different objects. We also have some, you know, again, the presets. So concave mirror, past the center of curvature. Concave mirror, between center and the focal point, and concave mirror at the focal point so you can't see it, and so on. And so you can use the presets or set them up. So that's what you can do for optics. Turn off the autofocus. We also have circuits. So so in circuits, we have a breadboard, and they can build any circuit they want using resistors, inductors, capacitors, light bulbs, and these wires on this breadboard. Any circuit up to 35 components. We have a function generator for sine wave, square wave, sawtooth, DC. We also have batteries, change its voltage, change its frequency, multimeters. We also have an oscilloscope. The cool thing here is that if you build it on the breadboard, then you see a schematic over here built. And if you build it on the schematic, it builds it on the breadboard automatically. So if I were to put, say, for example, my resistor here, and then I wanted to, I needed to bring my, like, my batteries up here, then I would attach them here, and then I could put my multimeter across here, and missed it. So now I can look at my multimeter and see what's my voltage, what's my current. My current's crazy because my resistance is crazy because I got current going through, you know. So amperage, you can measure current, and so you can do these. So you can do anything you want. So we're doing the complete Laplace transform here to do all the solutions. So here's, for example, charging a capacitor, or a preset, or holiday lighting with light bulbs with, you know, 6 hertz signal going on, and seeing how it changes the flickering on your light bulb. So circuits lets you do some pretty cool things as well. We have a density lab that's kind of built more for your high school, middle school, plus quantum, calorimetry, and gases. So how's that? Anything else? Anything you want me to demo?
From any section, what questions do people have?
It's a lot to take in. It all sounds so good. I think the best thing is jump in and just try some.
Yep.
Yep.
So
There was a ping for modern physics or biology. So we showed off the quantum lab earlier. I'm not sure if everyone is on at that point to be able to do photoelectric effect and show Rutherford and all of those. We didn't spend any time on biology though. Brian, do you want to do a quick walkthrough on bio?
all right, let me show the general chemistry instructors this inorganic lab as an example. I just usually want to show this. We have calorimetry, which I didn't show, which does bomb calorimetry, coffee cup calorimetry, heats of reaction, Hess's law, heats of solution. This inorganic lab allows you to mix any of these cations. So there's 25 cations. We show you a real picture. You can do a flame test and show you real pictures of that. You can decant, heat, smell, you know, smell it. You can add any of these reagents, any order, any combination, so that you can do qual schemes. So I can centrifuge that, decant. Now I've separated it. Now I can say add ammonia. I can centrifuge that, decant, and be left with my cobalt. I can add carbonate, for example, and get these different precipitates. So we have unknowns that you can do for qual schemes, and that. So just kind of wanted to show that off. And briefly for biology, Again, it's worksheets and lab benches, same idea. The idea behind biology, so I developed it with two colleagues, Keith Crandall, who's now at Washington, George Washington University in DC, and Riley Nelson, who's at BYU. What we did here is we wanted to do what modern biology is. So obviously biology is a lot of field work, a lot of collecting, a lot of categorizing, and there's lots of different experiments that we just couldn't do them all, but our focus here was on diversity. So we wanted to expose students to how we understand the diversity of species. So we created microscopy lab, a genetics lab, molecular biology lab, and an ecology lab to study species and how they behave or how they're the same and different at different levels, and then use a systematics lab to organize them. So in the microscopy lab, so I'll just go through this really quick. You know, we have different microscopes, TEM, SEM, compound dissecting field scopes, and we have a virtual world of about 175 species, and you can pick them. You can use this to organize them and select all of these, and then we show thumbnails of different images that you would see for these species from the different microscopes. So here's a video of paramecium. So they can see this, what it looks like for a compound microscope, and then move over to the SEM and say, wow, this is what it really looks like, you know, on an SEM. And so totally different view of what the species looks like. And so students can explore this. So we have a database of 3,500 different images and some animations as well in there, showing different processes. Here we have different species where we can do crossing and look at the statistics of the type of traits and phenotypes that get produced. So for example, I can look at pea plant, or I can look at fruit flies. Kind of cool because they have legs sticking out of their heads. You know, you could look at head shape with legs, and then you can randomize or set the genotype for each of the parents. So here I'm making it heterozygote, and then I can do a cross. So normally you get about 100 offspring per cross, and so you can show the statistics, how many male leg-headed, how many female leg-headed. And so here's a female. So there's a male. This is the second male. So there's one with the leg head sticking out of it. And so they can see the individual ones and look at statistics. So we have genetic models for everything. So we have epistasis, you have gene linkages, you have, you know, incomplete dominance, and all the different models you want, we have them in here. And so students can go explain it. So I got to move this so I can actually exit. So I don't know if you can see this. So there we go. So molecular biology, I'm not going to go do it, but so in molecular biology, we have primers and TAC and nucleotides. And what you can do is pick for any of these species, you can pick a DNA sample. So here's an epinorth tube, and I can pick that, and I can take a DNA sample from that. And what we did is we created a mini genome for each of these species. Some of them have about 20 genes, some of them have up to 100 genes, and random sequences in between. And what you do is you have to add your right materials. So we have instructions for all that. And then you can pick on your primers, and then you have to pick the right primers to amplify the right gene. You put it in your PCR, you amplify it, then you put it on your gel electrophoresis to see what it is, and then you put it in your sequencer and then sequence it. And you can end up, for example, with, that's a preset I picked. So here's sequences for ND1, for a fruit fly and one of them for a house fly, and compare and see how they're different or how they're the same. And so that's a way of doing that. Ecology is you can take species, and we have this abiotic variables that you can control for different biomes. Like here's tundra, for example, or here's your coniferous forest, and you can pick these different biomes, elevation, temperatures, pick species and throw them in and see what happens and see if they live or die or how they eat each other. So here's a wolf and an elk, for example. I click start, and then we show the populations as a function of time. So you see how elk, so see this is spring when they have their births, and then you see that elk are going down because there's a lot of wolves. The wolves are going up because they have a lot to eat. And then pretty soon here, they're going to crash. Elk are just going to crash because there's so many wolf. And then the wolf are going to crash because they don't have anything to eat. And then they're just going to start cycling themselves back and forth between what's going on. So move this again and exit. And then we have systematics. So in systematics, it's all about organizing. So again, here's your species selector. You pick a species. Then what you can do is say, okay, you can pick these different phylogenetic ways of organizing: 6 kingdom, a Linnaean, a simple scheme, a tree of the real tree of life. And so this is a simple 3-domain kingdom that might be in a freshman chemistry text. And what you could do is mouse over eukarya, and then it will say, here's the traits that you're looking for. And so you could, for example, if you wanted to, take the bat and go look for those traits in some of the others' labs. If you don't know what cytoskeleton is, you can click on it and we give a definition. And then what we do here is you can pick it. As you pick it, it puts species that aren't in that category in the discard pile, and you can work your way through it. So, so this is all about finding ways to organizing, see what's related to what. So that's the biology lab, a really quick overview. So any remaining questions?
Nobody's chiming in. Anybody else have anything else they'd like to see?
All right, are we done? Thank you for coming. I hope you could see all the things that you could do with the labs. And if you have questions, send us a note and we'd be glad to answer them as fast as we can. All right?
Good luck. Have fun.
All right.